Today we're going to talk about Lesson 1 from Algebra 2B Concepts, Exponential Growth and Decay. Before we get going, I just want to remind you that these videos assume that you have already viewed the lesson that we are going to be discussing. So for example, today I'm going to focus on a certain part of Lesson 1. So I am assuming that you have already logged into your course player and completed or at least partially gone through that lesson. The concepts I introduce will not be introduced entirely. It'll be more of a review, and again I'm going to focus on what I know to be the more difficult piece of the lesson based on the history of students who have taken it before you. So again, do not watch this video if you have not yet already logged into your course player and completed all or most of Lesson 1. This is meant to help you hone in on your Lesson 1 skills and focus on struggle areas once you've already been exposed to the material. If after you view this video you find yourself in need of additional help, don't hesitate to reach out to me. Remember, I also have a separate video library that's not worth credit but does contain several more in-depth videos that cover more lesson content and span a little bit longer. Let's get started. So again, we're going to talk about exponential growth and decay today, and our focus is going to be to create equations in one variable and use them to solve word problems. Looking at exponential graphs and linear graphs, you can see a big difference. I think this is often overlooked. For example, in discussion number 1, you're asked to give an example of exponential growth and/or exponential decay. Often students give me example of linear situations. For example, someone might say, every week I buy myself another pair of shoes. Well, that would be linear growth, because in week 1, maybe you already had 10 shoes. Then you bought yourself pair number 11, pair number 12, pair number 13, and so on. You can see how this is constant growth. Each week I'm adding one more, and the graph of this line is completely straight. Linear, right? The first 4 letters spell the word line. That's going to be the shape of that graph. This is the one you've been exposed to over the years when we've plotted things using y equals mx plus b. This was always the type of line that you saw. This is constant growth. Exponential growth, on the other hand, if you notice, begins very slowly and then quickly grows upward, or in the case of decay, quickly grows downward. So in that case, if I wanted to give an example of exponential growth, I really doubt that you are exponentially growing the size of your shoe closet. That would mean something like this. Rather than adding 1 every week, you would start by adding 1 pair of shoes, then you'd buy 2 the next week, then 4, then 8, then 16, then 32, etc. You can see each time I was doubling the amount of shoes I was buying, and as you can see, that would be very quickly become pretty unrealistic. So again, exponential growth is a special kind of growth. It's not constant. It is growth that begins slowly and then grows more and more rapidly as time elapses. Exponential functions are defined by this function, f of x equals b to the x, where b is a base or a constant and x is the exponent. Notice that this is different from what we are used to seeing. We've seen many equations in the past where we might have something that says x squared plus 2x plus 3 or x cubed or something like that, but it was always the case that x was your base. You never had an x in the exponent or a variable in the exponent. In the case of exponential functions, notice that x is always going to live in the exponent and not in the base. That's what causes this behavior to change and not be constant. So again, b will be our base, x, the variable, is our exponent. This is an independent variable. So what does that mean exactly? Well, diving in a little deeper, a function of the form f of x equals a times b to the x, where a is greater than 0 and b is greater than 1, is an exponential growth function. And on the other hand, if we have this same function where a is greater than 0, but b lies between 0 and 1, then we have a decay function. So what are we saying? Notice that this is just our basic exponent function, if you remember from the last slide. they've added a multiplier a onto the front. We're just saying it's multiplied by a non-zero number, and if the base is greater than 1, the function will grow. If the base is in between 0 and 1, the function will decay. If you think about this and test it out, it makes sense. For example, if I had 2 squared, I get 4. If I increase my variable, I get 8. If I increase my variable, I get 16. So as my variable increases, notice that the result also increases. Notice that this is a whole number greater than 0. However, if we look at numbers where the base is between 0 and 1, take for example 1/2. Let's do it here. If I square 1/2, I get 1/4. If I cube 1/2, I get 1/8. And so on. Taking it to the 4th power, I get 1/16. Notice that as once again I increased my exponent, the result got smaller. 1/4 to 1/8 to 1/16. The result is decaying. So it makes sense that if I'm raising a fraction to an exponent, it gets smaller over time, and these are going to be our decay functions. Let's practice identifying growth and decay. So for example, say we have f of x is equal to 9 times 1/2 to the x. Remember our guidelines for determining whether a function is growing or decaying. In this case, a would be 9, b would be 1/2. So is this growth or decay? Well, we've already verified that it's in this form, f of x equals a times b to the x. We've already verified that a is greater than 0. Now all we have to do is figure out if b is greater than 1 or if b is between 0 and 1. And obviously 1/2 is between 0 and 1. So if b is 1/2 and 1/2 lies between 0 and 1, then the function must show exponential decay. Another quick practice. Remember, key here is to determine the value of b because b is the thing that dictates whether we have growth or decay. In this case, the value of b is 5/4. Don't let seeing a fraction make you assume that it's less than 1. Notice in this case, our denominator is greater than our numerator, our numerator is greater than our denominator, which means that this value of this fraction is actually greater than 1. So b is greater than 1, which means we have exponential growth. So it's pretty easy to determine if we can identify b, pretty easy to determine whether our function shows growth or decay. Now on to the tricky part of this lesson. Using this formula, this growth and decay formula, and applying it to word problems. The first step is intimately understanding what each piece of this equation means. So let's take a quick look. A of t, this thing on the left side of the equation, is always going to be the final amount. It's what you end with. It's the total. You'll see keywords like that that notify you that that is the variable being spoken of in the word problem. This lowercase a in yellow is the initial amount. So if we were talking about money, this would be the amount that you originally invest, the amount of loan that you borrow. In other science examples, it might be the number of cells or bacteria that you start with, something like that. But a, this lowercase a, is always going to signify your starting point before anything has happened to the value. And this other a, capital A sub t, is always going to be what you end with after the process has happened. R is the rate of increase or decrease expressed as a percent. When you put the rate into the equation, it must always be converted to a decimal. For example, if they speak of a 5% increase, R would be equal to 0.05. T is the number of time periods that pass. This can be in any unit of time, days, weeks, whatever, it doesn't matter. This is a really unique situation. Often we have to be very, very clear about our units If you take other math courses, you will have time restricted. Maybe time must always be expressed in years or something like that. In this case, again, it's just the number of time periods that pass. So let's take a look at an example. Don't let these word problems intimidate you. My advice is to always at least read each word problem twice before you begin working on it. So on federal income tax returns, self-employed people can depreciate the value of business equipment. Suppose Doc Brown is doing his taxes, and a flux capacitor valued at $2,765 depreciates at a rate of 30% per year. Estimate the number of years it will take for the capacitor's value to be less than $350. Okay, so a lot of words. All we have to do is extrapolate the stuff that we care about. So reading this again, we know that we have a flux capacitor that is currently, so this is our starting point, valued at $2,765. So this is going to be the initial value of our function. Notice that I have written kind of the bones of the equation, the skeleton of it, and I'm just going to fill in. And I've even wrote myself a little roadmap. I've said, okay, I know n value has to go here, initial value next to it, then percent change, and finally time. I've already put a t in the time exponent because I'm being asked to estimate the number of years. So I know this is the variable I'm going to end up solving for. Alright, so continuing on. Reading this, I see that they tell me the capacitor's value, we want to know when the capacitor's value is going to be less than $350. So to me that means as soon as it's worth just 1 penny less, that's when we clock our time. So I've chosen the n value as $349.99 because that's when our capacitor is going to be worth less than $350. I've also already identified initial value as $2,765. Now I'm told it depreciates at a rate of 30%. So if we're depreciating, that means it's worth 30% less per year. So I'm going to subtract 0.30. Notice that I had to convert 30% to a decimal. So this is really the crucial part, just filling in each of these items into the equation. If you look at this again, I'm saying that I end up with $349.99 when I take my initial value of $2,765. I decrease it by 30% every time period. Now, when I plug this into the calculator, I find that my solution, t, is 5.8 years. So if you're wondering how I jumped from having this equation to automatically knowing the value of t, I chose to just plug this into a calculator and solve. And really there's no longhand way that is going to be convenient for you to solve this. If you're not sure how to plug this into a calculator, or if you just have questions in general about calculator computing, be sure to watch one of my videos on the matter. The most important thing is just going to be your order of operations, PEMDAS. Remember parentheses, exponents, multiplication, division, and then addition and subtraction. So I had to start by simplifying first in the parentheses, then taking the exponent, multiplying, etc. Okay? Again, if you're not sure how to go from having the full equation and getting to the solution, view one of my calculator tutorials. For now, we're just going to focus on setting up the equation correctly, which I believe is the most difficult step. So let's look at another example. Let's say that this year, Dwight Schrute bought a magic bean from Jim Halpert for $24 worth of junk. And let's say he invests this money in an account that pays 3.5% interest each year. He leaves the account to his great-great-great-great-grandchildren's grandchildren. Find the balance of the account in the year 2397. So one thing you might notice is that these word problems have a lot of fluff that we don't really care about. So for example, it doesn't matter to me that he left the account to his great-great-grandchildren, right? So I could cross that sentence out completely and it wouldn't affect the outcome. I recommend practicing recognizing what information is going to be important to you and what information is just there to kind of fill in space. So that being said, I'm just going to work this left to right once again, and I want to first kind of figure out what it is they're asking me to do. So notice that they're asking me to find the balance of the account in the year 2397. So which variable does that correspond to? Find the balance of the account in the future. Well, that's going to be my end value. So I'm solving for end value. I know that he initially invested $24, and the rate he invested them at was 3.5%. So I'm adding 3.5% converted to a decimal is 0.035. Finally, time I find by taking the year, which is 2015, and finding the difference between now and 2397. So that's going to be in 382 years. Again, because the interest is happening each year, notice it says pays 3.5% interest each year, I don't need to do any sort of conversion or anything like that. I know that there will be 382 time periods where the interest accrues, so I leave it like that. Finally, all I need to do is plug into a calculator. Again, if you need assistance with that, reach out to me or watch my video. So I find that after 382 years, after an initial investment of $24 with a 3.5% interest, he would have $12 million in the account. Alright, this will be our final practice before I wrap up the video. Let's say the Shire population, which was initially 4,000 hobbits, has been dropping by 2% a year. Write an exponential function to represent the situation. Predict when the population will drop below 2,700. Again, don't be intimidated here. Think about what you know and what you're being asked. So when they say predict when, you know that you're going to be solving for the time variable. They want to know when the population drops below 2,700, which is just another way of saying 2,699. In this case, I've left it 2,700. That insignificant difference is probably not going to affect the outcome of your answer, although 2,699 would have been more correct. So I know initially there are 4,000, so I put 4,000 for my initial value. The change is 2%, and the keyword dropping tells me I'm going to subtract. Notice that I've converted 2% to a decimal. Finally, all that's left is to plug this into a calculator. I'll make one more advertisement for my video on calculating using kind of complex expressions such as this. So take a look at that. And I find that time equals 19.5 years. So if you took this same expression and typed it into your calculator and did not get 19.5, go watch my calculator tutorial. Alright, so that's it for today. In summary, remember that exponential growth is a special kind of growth that's very different from linear or constant growth. Remember that a function of the form f of x equals ab to the x is going to be growing if b is greater than 1 or decaying if b is between 0 and 1. Also remember our growth and decay formula, our model, a of t equals a times the quantity of 1 plus or minus r to the t. Now, take a moment, go to my comprehension check, and complete the questions to earn credit for watching this video. If you have any questions, feel free to contact me via portal message, phone call, or however you'd like. I'd love to hear from you.